Hello and welcome to Lesson 5, the OSI Model and Protocols. Dialogue created and narrated by Don Kieber. Technology evolves, and the evolution of technology can certainly be attributed to many different organizations and the people within them. In the early years, very few standards and protocols existed between various manufacturers. So it became increasingly more difficult for users of technology to get interoperable systems when more than one vendor was involved. This has and continues to drive the need for technical standards that are considered open. Now, a technical standard is an established norm or requirement as it relates to a specific technology. When a technical standard is considered open, it's said that it can be shared on the open community and that its contents are not proprietary or secret. A standards organization is an entity whose primary activities are, among other things, developing, revising, and maintaining standards that address the interest of a wide base of users. One of the largest and notable standards organizations is the International Standards Organization. Now, as it happens, representatives of several major computer and telecommunications companies beginning in 1983 developed a model that originally was intended to be a detailed specification of interfaces. But instead, the committee decided to establish a common reference model for which others could develop detailed interfaces that in turn could become standards. Hence, the birth of the OSI, or Open Systems Interconnection Reference Model. The OSI model was officially adopted as an international standard by the ISO and is currently classified and defined under Recommendation X.200 of the ITU-TS, International Telecommunication Union, Telecommunications Sector. In this section, we will break this model down into its rudimentary elements and hopefully create a framework of understanding that you will take with you throughout your technical careers. We will demonstrate the OSI model's purpose through practical application, and we'll work to develop the concept of a layered approach to interoperability. And we'll see how specific protocols and services fit into the framework. We will also present real-world application through demonstrating how technology, equipment, and devices operate within the layers of this model. The OSI model has become ground zero for all network-related curriculum and is a staple in any technologist's toolbox. The importance of thoroughly learning and understanding this reference tool cannot be overstated. The OSI model, as described by the ISO Standard 7498, provides important guidelines that are used by vendors, engineers, developers, and others in an effort to create interoperable systems. The model is not, nor has it ever been intended to be taken literally. In many ways, the model is used as a tool to help communicate concepts to students of networking technology, sort of like what we're doing here. It's been said that the OSI reference model exists not to make hard rules or shape the industry, but to provide a logical, well-researched and tested model after which the world's best communication protocol stacks are modeled. Every layer in the OSI model is a reference for a protocol which must facilitate communications between both higher and lower layers. The U-shape of the model is intended to demonstrate the function of the design. So assume System 1, as pictured in this graphic, has data for System 2. The data, or payload if you will, starts at layer 7 on System 1 and begins its journey down the stack. The actual transfer won't happen until it reaches layer 1, the physical layer, but it must travel down the stack and have certain attributes called headers tacked on along the way. It happens that each layer will add layer-specific attributes to the payload data on its journey. When the fully modified payload data finally gets to the physical layer, it's able to be moved across the network to System 2. Now, when System 2 receives the modified data from System 1, it will send it up the stack, stripping off the attributes for each layer along the way. A core concept here is that each layer from System 1 will speak to its corresponding counterpart layer on System 2. The model visualizes a layer-to-layer design, but notice the actual data transmission doesn't take place until the bottom of the model has been reached. Let's take a look at the model architecturally. I will introduce each of the layers briefly at first, and then we will break them down individually in detail. There are 7 layers, and while there are many clever phrases for remembering these layers, I believe it best to start with a breakout of each layer individually and fully understand its role. Of course, you could still use a pointed phrase in the beginning to be sure you were placing the layers in the correct order. A famous phrase for this is, "All people seem to need data processing." As you can see, the first letter of each word is also the first letter of its corresponding OSI layer. Now, using a top-down approach, let's begin with the application layer. You could think of the application layer as the user interface. This is where the user application is running and where data is built around the application's capabilities. Moving to the next layer, we arrive at the presentation layer. This layer is responsible for translating from human to computer. You could think of this layer as an interpreter. It speaks to the requirements a networking process must have to adequately translate from what the user expects to see to what the computer expects to see. Below the presentation layer is the session layer. Once the data has been designated as transmittable and the translations or conversions have been completed, it has to be staged for a communication session. The primary function of the session layer is to manage and control the dialogue between external systems and devices. You could think of a communication session in this context as consisting of service requests and responses that occur between applications located in different network devices. Once a session layer dialogue has been established, a specific connection can be set up with the pointed information required to transport the data. The transport layer is where this happens. The jobs of the transport and session layers, respectively, are similar but not the same. The session layer is acting on behalf of the application data, where the transport layer is only concerned with specific connection information. These differences will be more clear as we proceed. Layer 3, the network layer of the OSI model, is where the addressing occurs. The network is home to, among other things, the Internet Protocol, IP, and the Internet Control Messaging Protocol, ICMP. Following the network layer of the OSI model is the data link layer. The link layer, as it's also referred to, provides the functional and procedural means to transfer data between network entities. There are also provisions in this layer to detect and possibly correct errors that may occur on the lower physical layer. At the bottom of the OSI model is the physical layer. The physical layer defines the electrical and physical specifications for devices. Specifically, it defines the relationship between a device and a physical medium. This includes the layout of pins, voltages, cable specifications, and the like. The upper layers 4 through 7 are considered host layers because they're focused primarily on host-specific duties, such as applications and data representation, inter-host communication challenges, etc. While the bottom layers 1 through 3 are referred to as the media layers because they are more concerned with the network-related issues such as addressing, routing, bridging, and the transmission medium involved in the connectivity of the endpoints. With that knowledge in mind, it's a good idea to consider where certain network devices are mapped. A router, for example, operates at layer 3, the network layer, and a bridge or switch operate at layer 2, the data link layer. Repeaters and hubs, which we'll cover a bit later, are mapped to the physical layer of the model. It happens that the OSI model is not the only reference model, and it is certainly not the original. An older and widely used reference is the TCP model. The TCP model was originally derived by the Department of Defense and breaks down into 4 layers rather than 7. In this graphic, you can see the relationship between these 2 models. The important thing to note here is beyond the fact that this model combines layer 1 with layer 2 and layers 5, 6, and 7 with each other, there is limited transport layer protocol support. It only supports 2 protocols, TCP and UDP, respectively. Recall that when System 1 had data for System 2, the data had to travel down the stack and have each layer add attributes in the form of headers. That process of adding or tacking on header attributes is referred to as encapsulation. The payload data is getting encapsulated with new layer-specific headers as it journeys to the bottom of the stack. It happens that layers 5 through 7, while adding certain attributes to the data, no real encapsulation is occurring. The process of encapsulation from the OSI perspective doesn't actually begin until the transport layer. The activities of the presentation layer are dependent on what the specific application is requesting. For example, if the application is requesting a graphic conversion, the presentation layer will perform that conversion prior to forwarding it down the stack. And if the application in question is requesting compression and/or encryption, then the presentation layer will handle that process as well. But for the purpose of clarification, if the presentation layer is involved with compression and/or encryption, it's possible that there will be some encapsulation happening, but the encapsulation, if any, would be outside the scope of this discussion. From the OSI model's perspective, the encapsulation process doesn't really begin until the data reaches the transport layer. With that said, the session layer, as we have seen, is a communication broker. While it's responsible for connection establishment, management, and teardown, it's not performing any form of encapsulation. I find it helpful to conceptualize the OSI references to encapsulation as a 5-step process. In step 1, the user information is converted to data, layers 5 through 7. Second, the data as it arrives at the transport layer is encapsulated with a transport layer header. Data in this form is considered a message. The messages are then segmented and passed on to the network layer for addressing. Third, these segmented messages, as they arrive at the network layer, are encapsulated with a network layer header. Data in this form is considered an IP datagram. The IP datagrams are packetized and may be fragmented as needed, and the resulting data from this process is referred to as a packet. In the 4th step, the packetized IP datagrams arrive at the link layer and are again encapsulated and possibly fragmented further. The resulting encapsulated data is referred to as a frame. In the 5th step, the frames in their final form are moved to the physical layer and streamed as binary bits onto the transmission medium. So to summarize this, a message is segmented at the transport layer and passed to the network layer to become an IP datagram. An IP datagram is packetized at the network layer and passed on to the data link layer to become a frame. And a frame is the fully encapsulated packet made ready for communication. So let's take a look at each of these layers in a little bit more detail. We start with the uppermost application layer. The key concept to remember is the application layer is not necessarily where the applications themselves work. The model was never intended to be an application specification, but rather where the protocols that support network functionality as they relate to those applications are mapped. The application layer works close to the user and provides protocols that enable file transmissions, message exchanges, terminal sessions, etc. Some well-known protocols that work at this layer are Simple Mail Transfer Protocol or Hypertext Transfer Protocol. There are others like Line Printer Daemon, File Transfer Protocol, Telnet, and Trivial File Transfer Protocol. So what this layer is doing is using application programming interfaces, or APIs, to integrate common network-based protocols with mission-specific applications. A good example of the functions of the application layer might be a user like Sam that desires a meeting with Charlie. So he uses his messaging program, possibly but not necessarily Microsoft Exchange, and composes his message to Charlie. Once he hits the submit key, the work begins. The application layer will incorporate the appropriate protocol, follow the rules of that protocol, and prepare the message for transfer. It's possible that the application may need to launch some kind of graph conversion or compression function. In this case, the APIs involved would incorporate the services of the presentation layer. The presentation layer is mostly concerned with data conversions, compression, and cryptography functions. The presentation layer receives information from the application layer protocols and puts it into a format that all computers can understand. This layer provides a common means of representing data in a structure that can be properly processed by the end system. So when a user constructs a Word document or an Excel worksheet and sends it out to several people, it doesn't matter whether the receiving computer is a Mac, Windows machine, some flavor of Linux, or Unix. Each will be able to receive this file and present it. The participating system will have a list of file types it understands and tables describing what programs should be used to open and manipulate each of these file types. The presentation layer is not concerned with the specific content of the data, but rather with the syntax and format of that data. You could think of the presentation layer as a translator, which translates the format an application is using to a standard format used for passing data over a network. Once the data has been made ready for its peer or peers, it's passed to the session layer. The session layer is all about relationships. A session cannot exist in the absence of a communication partner. The job of the session layer is to act as a moderator or communication broker that assists in the setup, maintenance, and ultimate termination of communications between two end systems. A good analogy for understanding the functionality of this layer is a telephone conversation. So when Alice wants to call her friend Bob, she uses the telephone. The telephone circuitry sets up the connection over the telephone lines and maintains that communication path. When Alice hangs up, the call is terminated, and all of the resources it was using to keep that connection open are released. The session layer acts the same using three distinct phases: establishment, transfer, and release. Some well-known protocols that are native to the session layer are the Network File System Protocol and the Structured Query Language Protocol. Additionally, remote procedure calls are native to this layer. Microsoft systems are rich in RPC mechanisms. Once a session has been established, the data is passed to the transport layer for end-to-end communication processes to begin. The transport layer provides end-to-end data transport services and establishes the logical connection between two end systems. The services of the session and transport layers may sound similar. It's true that they are both setting up some type of session or virtual connection for communications to take place. However, the protocols that work at the session layer are setting up connections between applications, while the protocols that work at the transport layer are setting up connections between end systems. For example, we can have three different applications on System A communicating with its counterpart applications on System B. The session layer protocols will keep track of these different sessions. The transport layer will see these sessions transparently and may treat them as a single connection. On the other hand, once an application has an established session with its peer on a remote end station, that session will stay intact until the application no longer requires communication with its counterpart. However, the transport layer could have multiple opening and closing connections happening within the single session. Each time a new connection is required, the protocols at the transport layer work to establish, maintain, and terminate those connections as needed. You can think of the transport layer like a bus. It's not concerned with the applications that are communicating with each other. It just provides the mechanism to get the data from one system to another. Just like a bus can carry a variety of people, the transport layer can carry a variety of types of application data. One of the ways the transport layer processes end-to-end data transmissions is via a process known as segmentation and reassembly. The transport layer takes the data received from the upper layer protocols and breaks it into segments that are sized in accordance with the maximum segment size of the network in question. The reassembly process will happen on the recipient system. The logical communications between hosts is sometimes referred to as a virtual circuit. Now, there are 5 classes of connection mode transport protocols ranging from class 0 through class 4. Some of the features within these classes include connection and connectionless orientated networks, segmentation and reassembly, error recovery, multiplexing, and explicit flow control. There are other features as well, and the various protocol classes will have these features enabled or disabled depending on the class. Some classes will overlap with enabled or disabled features of other classes, but there will be differentiators that separate them. There are even some cases where the transport layer protocol involved will have features outside of those offered within the specification. An example of that type is the very popular transmission control protocol. TCP, it happens, is very close to being a full Class 4 protocol, but it has been modified to include a graceful close feature that is typical of session layer protocols. As you progress through the layers of the OSI model, it will become evident that in many cases there is an attempt to draw a box around a specific network function, when in reality that function may not fit the box precisely. 2 of the many features supported in the transport layer protocols are connection and connectionless orientated. In a connection-orientated protocol such as TCP, the connection state is constantly validated with acknowledgments. These acknowledgments are sent from the recipient system for every connection stream created. Additionally, when a connection-orientated protocol is used, there is a handshaking process that takes place to establish the connection. This is not the case for connectionless-orientated protocols. A connectionless protocol, such as UDP, will simply send its data without the need for acknowledgments, and hence there is less overhead associated, but no guarantee the data will arrive intact. The primary functions of the network layer are to tack on an address and route the packet. One very important consideration when thinking about the network layer is the routing process itself. Routing makes it possible to communicate with networks outside of the local network. In a network, many routes can lead to one destination. The protocols at the network layer must determine the best path for the packet to take. There is a clear distinction between 2 similar sounding and yet completely different network layer functions: routing protocols and routed protocols. Routing protocols build and maintain routing tables. A routed protocol is any protocol that uses the routing process to communicate with its peers. A routing table is a map of the network or networks known to the system. When a packet needs to be sent from System A to System XYZ, the system will check its resident routing table for a path. If a path is not known, there will be a default path configured that will serve as the next location to check for the path information. As I indicated, the routing protocols build these tables, and the routed protocols use these tables to establish a path to their intended peer. An important consideration is that the protocols that work at this layer do not ensure the delivery of packets. They depend on the protocols at the transport layer to catch any problems and resend packets if necessary. Internet Protocol, or IP, is the most popular protocol working at the network layer, but there are other routing and routed protocols mapped to this layer as well. Some other network layer protocols include Internet Control Messaging Protocol, ICMP, Routing Information Protocol, which is known as RIP, Open Shortest Path First, an acronym of OSPF, Border Gateway Protocol, which is known as BGP, and Internet Group Management Protocol, or IGMP. So now that we have addressed and set up the proper routing of our data, we need to build this data up for the actual transmission. The primary concern of the data link layer of the OSI model is to establish a framing technology that is compatible with its network peers, break the data into frames, and format it for the physical medium. The primary concern of the data link layer of the OSI model is to establish a framing technology that is compatible with its network peers, break the data into frames, and forward it to the physical medium for the binary transmission to begin. Framing technologies could be LAN-based or WAN-based. Examples of LAN-based framing technologies are Ethernet, Token Ring, and FDDI, or Fiber Distributed Data Interface. Additionally, 802.11 wireless LANs operate at the Layer 2 of the OSI model. Some examples of WAN-based framing technologies include High-Level Data Link Control, or HDLC, and its predecessor, Synchronous Data Link Control, or SDLC. Additionally, there is Frame Relay and X.25. A very important aspect of the data link layer, though, is how it's broken down into two functioning sublayers, the logical link control layer and the media access control layer. Much documentation regarding the data link layer describes it in terms of these two sublayers. The uppermost is the logical link control, or LLC, sublayer. This sublayer essentially multiplexes protocols running at the data link layer and optionally provides flow control, acknowledgement, and error notification. The sublayer below the LLC is the media access control, or MAC layer. Sometimes this layer is the sublayer that determines who is allowed to access the media at any given time, typical of CSMA CD designs. Other times it refers to a frame structure with a MAC address inside. In this graphic, a clear distinction of these two layers is visually illustrated. Note the mappings of the LLC and MAC layers within the model and how the MAC and LLC headers are prepended to the packet as separate headers. So a packet is encapsulated within an LLC and MAC header to become a frame. The frame is then forwarded to the physical layer for transmission on the medium. And we're finally here. The data has made it down the stack and is now ready to be transmitted on the physical medium. Layer 1 of the OSI model converts bits into voltage patterns for transmission. It's crucial that you understand signals and voltage schemes have different meanings for different LAN and WAN technologies. If a user, for example, sends data through his dial-up software, out his modem and onto the telephone line, the data format, electrical signals, and control functionality would be very different than if that user sent his data through a network card and onto an unshielded twisted pair or UTP connection to communicate on the LAN. The physical layer is really two components operating in tandem. First, the signaling component, which interfaces with the underlying logical data structures of the higher level functions in the network and performs character encoding, transmissions, reception, and decoding functions. And second, the physical medium component that defines the means of transmitting raw bits of data into the transport medium. So while the physical layer has to interface with the data link layer protocols to receive and transmit frame data, it must also support a plethora of physical medium technologies with widely varying characteristics dependent on wiring or radio communication paradigms in place on the system. The actual transmission of data onto the transport medium is streams of bits grouped into code words or symbols and converted to a physical signal that is transmitted through the hardware interfaces. The bottom line is everything winds up as binary data, ones and zeros, and streamed onto the transmission medium. By keeping the functionality of the physical layer subdivided, it makes it possible to develop technologies having to do with logical aspects of a network independent of the development of physical medium standards. Many equipment manufacturers, especially router and switch companies like Cisco and Juniper, create special interfaces that are considered media-independent interfaces. Using these special interfaces, you're able to choose from a multitude of physical medium-specific transceiver options to properly match your physical medium deployment. A concept known as network topology is used to describe the architectural layout of a network. This is used to describe the physical connections of the systems and devices as they are grouped within a network. There are several well-known topology types that you will run into, including the bus topology, in which all systems are on a shared medium like a coaxial cable. Initial implementations of Ethernet were based on this design. Another is the ring topology, in which systems are configured in a circular ring. The token passing systems use a ring topology. A very common topology in use today is the star topology, in which all systems have a dedicated cable segment and are aggregated at a central device like a switch or hub. Unshielded twisted pair is an example of this model. There are other topology designs as well, including a tree and mesh design. The topology choice typically depends on the logistics of the locality or localities involved. For example, a multi-story building may use a sort of tree topology in which each floor incorporates a star topology, and then the floors are connected through some form of uplink trunk. It's important to understand that where a topology type may suggest or even dictate a physical medium, it's not the actual physical medium. Hence, a network topology is comprised of a logical and physical component. Physical medium examples are numerous, but here are a few to help cement the concept. 10^-T describes an unshielded twisted pair physical medium, and 10^2 describes a coaxial cable physical medium, typical of the legacy bus topologies, while IEEE 802.11 describes the physical medium of a Wi-Fi standard, and 100BASE-FX describes a fiber optic physical medium in support of fast Ethernet. Additionally, USB and FireWire, DSL, and ISDN are all considered physical medium standards. Okay, so now that we've worked our way through the layers of the OSI model, there are a couple of concepts to review. The first deals with the transport layer services and has to do with the conceptual use of ports. TCP and UDP, for that matter, use the notion of port numbers to identify sending and receiving application endpoints. Each TCP or UDP connection has an associated 16-bit unsigned port number, 0 through 65535, reserved by the sending or receiving application. It happens that arriving data are identified as belonging to a specific connection by their sockets. The combination of source and destination IP address plus the 16-bit source and destination port numbers make up the connection identifier known as a socket. The concept of sockets make it possible for a server to provide several clients with several services simultaneously, as long as the client takes care of initiating any simultaneous connections to one destination port from different source ports. Port numbers are typically grouped into three basic categories: well-known, registered, and dynamic private. Well-known ports identify well-known applications like SMTP, HTTP, Telnet, and DNS, to name a few. So applications like the ones I just mentioned are not running at the transport layer, but rather are identified at the transport layer through the use of the port assignments. It's important to understand the offsets within the transport layer header and where the port numbers are set. Within the header, there is a concept known as a bit offset. The bit offset represents the relative position or starting point of a specific field. It happens that the source and destination ports, each 16-bit, are located just before the sequence number at offset 0. Each of these fields has special and specific roles within the header, but a detailed discussion on these fields is beyond the scope of this course module. I do challenge you, though, to get a thorough understanding of the field roles and attributes within the transmission control protocols. One more concept to review is a summary of the protocols and services as they relate to their relative positioning within the OSI reference model. This graphic illustrates this concept and is a great study tool. The protocols referenced here are not a full comprehensive list, but rather a well-known subset of them. This graphic further illustrates this concept and shows the protocols in a more hierarchical layout. Again, this illustration does not present all of the possible protocols and services, but it does show the most common ones. So this completes the audio dialogue associated with Lesson 5 of the OSI model and protocols. In this course module, we discussed how the OSI model came after the TCP model and has a much broader scope. We also saw how the OSI model is used by developers to build protocol specifications in a modular manner. Additionally, we demonstrated how each of the OSI layers has specific functions, features, and capabilities. We saw how various protocols and services work at different layers in the OSI model. And we demonstrated how certain networking devices have been built around specific layers of this OSI reference model. Our next lesson is the IEEE 802.11 standard.